Hello, I'm Narjit Singh and this is the presentation on prognosis and health management using energy activity. Let us start with the basis of maintenance, which is the process of preserving the condition of a system. The most primitive strategy for maintenance is maintenance after fault, called the corrective maintenance. In this strategy, as the maintenance is performed after the occurrence of a fault, it leads to loss in working hours. Therefore, another strategy is used called the preventive maintenance, in which maintenance is performed at regular intervals. However, it can lead to monetary losses as many times maintenance is performed even when it is not required. Therefore, condition-based maintenance is proposed. In this strategy, maintenance is performed only when it is actually required. Condition-based maintenance is achieved using prognosis and health management. Let us now understand the PHM process. The first part of the process is data processing, which deals with signal acquisition and signal processing. The next is system health estimation. System health estimation has three components: fault detection, isolation, and diagnosis. Fault detection deals with checking the presence or absence of fault. Isolation deals with locating the fault in the system, and diagnosis deals with finding the nature and cause of fault. Further, we have prognosis. The purpose of prognosis is find to end of life time of the product, that is the time at which the product will fail given the conditions of fault. When we have the end of life, we can find the remaining useful life, which can be used for decision making. The main components of PHM process are system health estimation and prognosis. Both of these can be done by data-driven techniques, model-based techniques, or hybrid techniques. Irrespective of the technique used for PHM, the following are the major challenges: the representation of degradation model and failure criteria in terms of the prognostic parameter. The degradation model and failure criteria are easy to define in the design stage, but this stage deals with the numeric value of system parameters and not with the prognostic parameter itself. Therefore, a parameter that can map these to system component values will be easy to use. Another challenge to PHM is due to the complex nature of the systems. Systems have multiple domains of physics interacting with each other. They are governed by different laws. For example, electrical system is governed by the Ohm's law, but mechanical systems are governed by Newton's laws. However, all of them do follow the law of conservation of energy. So, a prognostic parameter based on energy is beneficial. This need has been recognized and work has been done on it. Also, total energy consumption, due to its ever-increasing nature, is found to be more suitable for prognosis. But this has some drawbacks. That is, energy is calculated on system as whole and not at component level, for which degradation model and failure criteria are more known. So, a prognostic parameter should be energy based and should be applicable at component level. Health estimation and prognosis are closely related to each other. Therefore, a common parameter for both of them is desirable. However, there is a fundamental difference between the two. When performed individually, health estimation is done using the concepts of FDI, which assumes that the initial conditions of the system are unknown. However, for prognosis, full or partial knowledge of initial condition or non-faulty condition is assumed. So, extra information available in prognosis stage could be used for health estimation. So, in this work, energy activity is proposed as metric for health estimation and prognosis because it is an always increasing energy based indicator that can act at component level and can use component values as failure criteria. Also, the initial conditions that are known can be used for health estimation using energy activity. Let's understand the difference between energy and energy activity. Energy is the integral of power, but energy activity is the integral of the absolute value of power. So, understanding it using an example, let a component undergo a power consumption according to the given profile. For the same, the energy is given as this curve, but the energy activity is like this. Therefore, it is the amount of total energy interaction the component has undergone. As the total interaction always increases with time, the energy activity also always increases and it never decreases with time. Let us also understand the concept of activity index. While energy activity is the total energy interaction of a component, the energy activity index is the interaction of the component relative to the total interaction of the system. Therefore, the energy activity of a component gives the absolute picture of the interaction of an element, but the energy activity index of an element gives the relative activity when measured with the system as whole. Calculation of energy activity is very easy and direct using bond graphs, as energy activity is the integral of the absolute value of power. Power of an element can be directly calculated using bond graph as product of effort and flow related to that element. The energy activity can be found using this equation. In this equation, S is the signal input to the element, phi is the numeric component value of the system, and Gs represents the constitutive equation that governs the element. Energy activity calculation can be better understood using this table. Based on the causality, the signal input to an element changes. This changes the form of constitutive equation that governs the element and therefore the equation that is used to derive the power. Let us understand the PHM procedure using energy activity. First of all, we have the systems. We have a real system that can undergo a fault and a simulated system. For signal processing, the simulated system does not require any form of signal processing, but the real system must be filtered for noise. The outputs are used for system health estimation. First of all, the energy activity is calculated for both the systems. The difference between them is used for fault detection. Once a fault is detected, the energy activity indexes are calculated for both. The differences between the energy activity index and a pre-trained neural network is used for fault isolation. Once fault isolation is performed, we have all the things required for prognosis. Noise reduction is a must before calculation of energy activity. The noise is assumed to have much higher frequency than the signal itself, and the signal to noise ratio is assumed very high. So in this case, signal processing can be done using Fourier transformation. The Fourier transformed signal is removed for high frequency and low amplitude peaks. Therefore, the noise is removed. After signal processing is system health estimation using energy activity. Energy activity is used directly for fault detection, after which isolation needs to be performed. The input to the element S depends only on the measured values, but the structural relationship is not utilized for energy activity calculation. Therefore, any change in measurements due to fault will change the energy activity everywhere. Therefore, traditional fault signature metrics cannot be used. But it must be inferred that a fault reconfigures the energy interaction between the elements of the system, also affecting the speed of the energy interaction. This change in speed will reflect in the energy activity index, and an FFT analysis can give us signatures of specific faults which lead to some specific changes in energy interaction among the elements. These signatures can be put in a classification algorithm for proper fault isolation. In the current work, neural networks are used for classification. The creation of neural network database is done using iterative process. The system is simulated many times under the following conditions to create a neural network database. Residuals are generated as a difference in the energy activity index of real and virtual system. Fast Fourier transformation is performed on the generated residuals, and the peak locations are recorded and used in neural network. The flowchart shows the iterative process for neural network data generation. Neural network is trained using the peaks of the FFT analysis of residuals. Therefore, to match, an FFT analysis must also be done on the measured signal. As the signal is continuous, short time Fourier transformation is performed. But it must be assured that the integration window for calculation of energy activity must be larger than the time interval used for short time Fourier transformation. After isolation, we move to prognosis, which is the key part of this. The component degradation rate can be found using energy activity, which can be integrated in time to calculate the actual component value at a particular time. Energy activity calculated at a resistance element in the bond graph is used for prognosis. The sensitivity of energy activity to the signal input of an R element can be calculated as shown. Continuing from the previous equation, the component degradation rate can be calculated as shown. In this equation, the derivative of energy activity can be measured from the energy activity of real system. The partial derivative of energy activity with time means the derivative of energy activity under no fault condition. This can be measured using the energy activity from the simulated system. The sensitivity of the input signal to the component value can be calculated from the dynamic model. The above equation can be integrated in time to find the component value at any given time. Let us consider a spring mass damper system as an example. First of all, the neural network needs to be trained. The figures show the Fourier transformation of the residuals for energy activity index measured at different locations under faults at different locations. It can be seen that for every fault there is a unique signature in the frequency domain. This signature can be used by classification algorithms for proper fault isolation. The spring stiffness undergoes a change in component value, that is a fault, and thereafter a maintenance action is performed to revive the component value back to its original form. This figure shows the spectrum of short-term Fourier transformation. Once fault isolation is performed, the prognosis is performed using the given equation. The figure shows the calculated component degradation rate. The component degradation rate is integrated to find the estimated spring mass, the spring stiffness over time. It can be seen that the estimated stiffness has very less error. Therefore, the prognosis is very correctly done. Conclusion: energy activity is proposed as metric for health estimation and prognosis. Fault detection is performed directly using energy activity. Fault isolation is performed using energy activity index and neural network. Prognosis is performed again using energy activity only. The method is simulated on spring mass damper system, showing good results. Thank you.